Hi, I decided to do a video on one of the 7.7 homework problems. I don't know if you need it or not, but there were a couple things that I did just to make it make more sense that I wanted to make sure you guys thought of. So they gave us a differential equation and an initial value, and so we're starting at the 0.02. And since our delta x is 0.2, you can easily add, you can easily add, and just make this 0.2, 0.4, 0.6, 0.8, and then 1.0. So you can do those no matter what. And then as you're calculating the things for the next two columns, you remember you're using the previous point. So you're using the 0.02 to calculate this right here would have been your dy dx, and then you're multiplying that by your delta x. And so this is 0 times 0.2, so this is going to be 0, and then you're adding this 0 plus your y, right? This is like your y plus your delta y. And so you get 2 again. And so now you've got the 0.2 comma 2. And then you go to the next one, -3 times, this time you're using that point. And so that's your x value, that's your y value. This is your dy dx, and again, you're multiplying by delta x. So this is going to give you -0.24 times 0.2, and that's going to give you -0.048. And then you add that to your y value, add those two, and 1.952 is your new y value. So your new point is 0.4 comma 1.952. And now you're using that point, -3 times 0.4 squared times 1.952 times your delta x of 0.2. So this right here is your dy dx, and you should have gotten -0.93696, and then times your 0.2 should have given you that gives you a number, and then when you add that number to 1.952, you get 1.764608, okay? And so same thing goes, this number, I'm just going to write the number this time. This one would have given us, after we did all that above, -0.381155328, and then we would have added it to our 1.764608, and we would have gotten a new y value of 1.383452. And then done the same thing here, we should have gotten -0.5312458, and added that to our previous y value and got 0.852206. Okay, so that would be our approximation for y1. So right now, the whole reason we did this is we're saying, hey, y1 is approximately this using, Euler's method. And so then it wanted us to sketch these points. And I don't know, I did not have a good time sketching these. This is point 1, point 2. So point 2, we had also 2. And then point 4, we had 1.952. And then point 6, we had 1.7. So that's probably about right there. And then 1.8, 6, 7, 8. We had 1.3. It's about right there. And then 1.0, we had 0.85, which I don't know, about right there. And so you can either do them with like, what do you call it? Line segments, or you could do it just by, connecting them and putting like a little function in there, like they were a function. This is not going to be your actual function, but it's a kind of an approximation for it. And so now they want us to solve that differential equation. And so I would divide by y and leave my dy there. I would multiply by dx and leave my negative 3x squared there, and then integrate both sides. So ln, absolute value of y, is equal to, and what I did is I pulled that negative 3 out, and then I integrated x squared plus c, and then my 3's canceled. Okay, and then I put my initial value in. I put my 0, 2 in. And if you put 2 in for y and 0 in for x, you can see that your c is ln 2. And so now that gives you that ln, absolute value of y, equals negative x cubed plus ln 2. And I'm just going to make that a little bit smaller and do the rest over here. So now you can take e to the power on both sides. And of course this becomes y. This becomes e to the negative x cubed times e to the ln 2. And then e to the ln 2 is 2. We're going to move that in front. And this is your solution to your differential equation using that particular starting point or initial value. And so then when it says compare the two values, does your estimate in part A overestimate or underestimate, explain, you would have to be thinking about whether it's concave up or concave down. And you can see that your approximation using Euler's method is concave down, but to get actually the proof, you would have to take the second derivative and find those critical points. So if we took the first derivative here, it would be 2e to the negative x cubed times the derivative of negative x cubed, which would simplify to negative 6x squared e to the negative x cubed. Okay, so that's our first derivative. Then we would take our second derivative. Well, we'd have to use the product rule here. So this is first times the derivative of the second. So the derivative would be negative 3x squared e to the negative x cubed, and then plus the second times the derivative of the first. And so that second derivative would simplify to 18x to the fourth e to the negative x cubed minus 12x e to the negative x cubed. And this is the one that you would want to look and say, well, I can factor a 6x out of that, or actually a 6x e to the negative x cubed out of that. That would leave me with 3x cubed minus 2. And then, of course, x equals 0 would be a critical point. And if I set my 3x cubed minus 2 equal to 0, 3x cubed equals 2. X cubed equals 2/3. And so x equals the cube root of 2/3 would also be a critical point. And so at that point, you could say, okay, I've got 0 and I've got the cube root of 2/3, which if you put that in your calculator, it's like 0.87358. And then if you looked at y double prime, the sign of it, I just put this function in my calculator and looked to see when it was above the x-axis and below, and it was above it to the left of 0, it was below it to the right of 0, and then it went above it again after that critical point. And so you can see that it's concave down from 0 to 0.87358. And so whenever they wrote about it, I think they said something like, part A over estimates since f of x is concave down on, and I was wondering if you were wondering where this 0.87358 came from. And so I wanted to show you that this is where that came from. You could have also found it by putting that second derivative into your calculator and calculating it. You know, I just did it algebraically here, but you could have also done that using your calculator, but you still would have had to have that function. And then it went on to say that the tangent line lies above the actual function, but does say that it's an overestimate. And then it asks you to find that error at the end, and you just took the absolute value of, because up here, I forgot that I was supposed to find my y of 1 once I found my function here. So my y of 1 was 2 times e to the negative 1, which was 2 over e, which was 0.3575. And so this was my actual minus my approximate. Oops. Absolute value. Which gave us that 0.116456. Okay, I just wanted to work that one problem. If you need any others, just